Check, check. Okay, now it's on. Okay, I was even muted. Okay, so I'm gonna hop over to the first problem. It's going to be like exploring impulse response of these various components. So let me draw out our circuit real quick. It's gonna look like this. We're gonna like this. This is our resistor to our inductor, and you know, to our capacitor. Ah, man, that's good enough. Really trying to get a good drawing so I can please you guys. So there's some level of satisfaction. And then we have a voltage source, Vn. And it's time-dependent voltage source, so it changes over time. Except we're going to be working with an impulse. So it's going to go from 0 to 100. Well, not really 100, but 0 to some magnitude. In this case, it's 1 volt second is the unit of impulse. So we're just labeling everything that's important when we're doing the schematic. Positive, negative, we're going to always label that. We're going to label our positive and negative to understand the flow of the current. This is also time dependent. Because our input is time dependent, everything else, any other voltage is going to be time dependent. Consider the circuit shown above in which Vn of t equals 1 volt seconds. I'll put out all our knowns so that it makes it easier for us to find our unknowns. We want our impulse looks like this. Vn of t equals just one, and then this is what the symbol for the impulse function looks like. It just looks like that, of t, and then volt seconds, but we're just gonna put vs like that. That's volt seconds. That is, Vn is a unit impulse at time t equals 0. Right at time t equals 0, we go straight to 1 volt. 1 volt. It happens instantaneously. That's the thing about the impulse. And so we're going to see how this circuit responds to an instantaneous jump in voltage. Such as L is the inductance of our inductor right here. L equals 5 millihenry. 1 equals 10 ohms. Here, we'll write it. Yeah, R2 equals 10 kilo ohms. C equals 33 nanofarads. That's our capacitance. 33 nanofarads. Alright, that since the circuit is driven by an impulse and there is no other source of energy, the capacitor voltage and inductor current at t equals 0 will be 0. But we're also going to define that. We're going to put that down. So Vc of 0 at 0, once the impulse happens, equals 0. And then IL, the current through our inductor at time 0, also equals 0. See where we at. What is the value of VR1 of t at t equals 0 negative in volts? Say, what is the value of VR1? So the voltage across R1 at t, at just the instant before t equals 0. Define our impulse, and let's put it on a graph. Let's like, this is our x-axis, right? That's our y-axis. Our y-axis is going to be the voltage. This is going to be our time axis. We're going to define it at 1 volt. You know, we're not working with huge numbers here. But you will see that... by applying an impulse to the circuit we're about to analyze, by applying an impulse to this circuit, you get some incredibly large numbers. Right here, just at t equals 0, we're going to get this impulse. So I'm trying just to give some insight that this is the impulse function in something for t, and it's 0. This is just like when you have a negative, it means just the instant before t equals 0. If it were a positive, it'd be the instant after t equals 0. So just moments before t equals 0, we have no input into the circuit. There's no voltage. Therefore, there's no current. Therefore, the voltage across R1 is just going to be 0. The impulse hasn't occurred yet, just moments before. R1 of 0 positive equals. Okay, so now we're actually going to start crunching some numbers, get into the calculation. But a lot of this right here actually comes down to like a logical analysis. Okay, we want to know the voltage across R1 just moments after the impulse had occurred. Okay, so we have a voltage impulse. Therefore, the voltage impulse is going to define the magnetic flux. Voltage has a relationship to electric fields, and these electric fields have a relationship to magnetic flux. in particular to the inductor. Okay, here we are with the inductor. Oh, nothing showing. No, that's good. All right, let's just think of this one in particular. This one has an iron core, ferrite core, and that's going to change the properties of the inductor. But let's a coil of copper. When a current flows through the inductor, a magnetic field is generated. And this magnetic field builds up as the current flows, and then when the current ceases, the magnetic field breaks down and puts out current in the opposite direction of. And this voltage impulse is going to induce a magnetic flux through this inductor. Okay, so I know that the current through the inductor is equal to this magnetic flux divided by the inductance, which is the inductance is just like the inductance is defined by the physical properties of the inductor. So like the number of turns it has is the thickness of the wire, it's the length of it, stuff like this. This is going to determine the inductance. So now we want to know the voltage across to R1, and by Ohm's law, we know that I times R equals V. Okay, those two branches are decoupled. So now, considering that these are decoupled, we're going to have the same amount of current flowing through both of these components. Okay, so IL times R1 is going to give us VR1. And we just plug in this magnetic flux divided by L multiplied by R1 equals VR1. The magnetic flux, because we have a voltage impulse, is directly proportional to the voltage impulse. 1 volt second divided by 5 millihenry multiplied by 10 ohms, okay, is going to equal VR1 millihenry. So we got 1 divided by 5 E. I'm going to use E, but you could also say times 10 to the negative 3, but I'm thinking we got 200. We're going to multiply that by 10 ohms, and that's going to give us the voltage across the resistor. Applied an impulse of 1 volt second, and we're going to get a response of 2000 volts across R1. Okay, no, that's kind of decent, right? You forgot what I was doing. Okay, so that's the answer to that question. What is the value for VR1 of t at t equals 1 millisecond? Okay, so let's draw it in a different model. We're going to simplify it, right? These are decoupled. These two branches are decoupled. So, all right, so we can say that these two elements are in parallel. They're in parallel. They share the same current this way, current this way coming out of this node right here. They're constitutive laws. Okay, so let's write down the constitutive law for the inductor. So we can write it down like IL equals 1 over L times the integral of VL, L times the derivative of IL over with respect to time. With respect to time, it's a derivative. Okay, so another way we could do this is by KVL, Kirchhoff's voltage law. So we're gonna say VR minus VL equals 0, VL. So now we'll plug in this variable. We're going to play it out. L dido minus VR equals 0. Okay, but that's how we define it. If we're going to define it in terms of current. Isolate this di with respect to dt minus divide by L because we want the derivative by itself. So it's going to be I times R over L. Is going to look like that, still equal to 0. Now, the way these first order linear equations work, we're going to assume that I equals A times E to the power of ST because we're going to assume this answer. So now if we plug this in, we're just going to go ahead and jump a step. We're going to pull out the A, we're going to pull out the E to the power of ST times E to the power of ST equals 0. Okay. That's supposed to be plus. Yeah, definitely plus. Okay, anyways, continuing forward, S equals negative R over L. I, L of T equals A times E to the power of negative T R over L. Okay. So it's going to look something like that. We're going to define A by our initial conditions. So IL, can you see this end? Yeah. Wait, so IL of 0, that's at the time of the impulse, equals lambda over L. That is true. IL of t equals lambda over L times e to the negative t r over L. We don't have a particular solution because we don't have a drive. Times e to the power of negative 0.001, that's 1 millisecond, times our resistance of 10 ohms divided by 5 e to the negative 3. Now that's our current. Okay, well, we figured out our current. You know, both components experience the same current. So this is our current at 1 millisecond after the impulse had occurred. R1 at 1 millisecond, 7 amps times 10 ohms. And so this is going to be VR1 at 1 millisecond, 270 volts. And that is correct. What is the value of the capacitor voltage at t equals 0 positive, just a moment after the impulse had occurred? Okay, it's just going to be a resistor in parallel with this capacitor. Okay, now we have the application of the impulse. The capacitor is going to look like a short circuit. So if all the impulse falls over the resistor, we're going to have the impulse itself, which is 1 volt second. Here, I'll write that in a different way. 1 volt second. And then this is going to be divided by R2, which is 10 kilo ohms, which is 10,000 ohms. 10 kilo ohms. And this will give us our current, remember, referencing Ohm's law. This will be 10 milliamps. So that's how we'll write it. We'll write 10 milliamps. VC equals the charge divided by the capacitance. So the impulse across the resistor determines our current, and the current is proportional to the charge. Q actually equals the current, or like the current with respect to time. But since we have an impulse and things are happening instantaneously, we can simply define the charge as being directly proportional to I. Because things are, it shouldn't be 10 milliamps, my bad. It should be 0.1 milliamp. 0.1 milliamp. Okay, so let's just write it 1 e to the negative 4. That's a 0.1 milliamp divided by 33 e to the negative 9. Okay, that's our answer. So the voltage across the capacitor a moment after the impulse is 3030 volts. Okay, so that's our answer for the voltage across the capacitor at t equals 0 positive, just moments after the impulse had occurred. Okay, what is the value for VC at t equals 1 millisecond? Right, okay. So similar to how we define the inductor by its current, we're going to define the capacitor by its voltages. Let's go ahead and define the first order linear differential equation. Yeah, described by the current. So we have IC plus IR equals 0. Equals 0. Okay, so now we're going to plug in our constitutive law for IC equals C times the derivative of the voltage VC with respect to time. We're going to define the current through the resistor by its voltage and resistance equals 0. Okay, again, we want to get the derivative by itself, so divided by RC. Again, we're going to assume the solution. Just go ahead and pull the similar terms out, and we're going to put our derivative as S 1 over RC times e to the power of ST equals 0. Therefore, S equals negative 1 over RC. Okay, we'll plug that in now, and then by initial conditions, we'll find our coefficient. EC of t equals 0 equals, let's say Q over C times e to the negative t divided by RC. Plug that in. 3030, 3030 times e to the power of negative 0.001 divided by 10,000, right? 10,000 times 33 e to the negative 9. VC of 1 millisecond after the impulse had occurred. And we're going to have 146, leave it there, volts. Okay, so it's obviously a decay. Obviously, the impulse occurs and we instantaneously have 3030 volts across the capacitor. 1 millisecond later, we've decayed down to 146 volts. Eventually, it'll decay down to 0. We define the other circuit, the RL circuit, by the voltage across R1. We initially had 2000 volts over R1, and then 1 millisecond later, we decayed down to 270 volts. There you go, ladies and gentlemen. Let's see. Exploring impulse response of a capacitor and inductor, time analysis of MOSFETs with parasitic capacitance and first order linear circuits. End it here. All right, cool. Thanks for tuning in, guys. I think I'm gonna work another problem, but I'm gonna hop on X.